I'm sure that some of you have heard the term hydraulic fracturing, also known as fracking. If you don't know what it is, it's a process that involves water, sand, and chemicals, and this mixture is pumped into the ground at extremely high pressures to expand cracks that have been previously made, to allow natural gas to flow freely so that it's easier for us to extract it. This is an extremely complex topic involving controversy, and it requires a lot of time and even more manpower. But before we can get too far into this, we need to understand the very, very basics of this, which is the drilling itself.
Hi, I'm Kelly.
I'm Chantel. And I'm Gabby.
We're going to be talking about well basics. Directional drilling, it's been around since the 1920s. With the technology evolution since then, directional drilling wasn't just like vertical anymore. Directional drilling today allows more holes to be drilled out of the same wellbore, like that, like a jellyfish, sort of. With the help of GPS units and drilling sensors, directional drilling has never been easier for oil engineers. Today the angle of the drill bit is controlled with new industrial technology that provides the company with multiple solutions for drilling challenges, which also minimizes the cost of building another well. Very cost efficient. Another type of directional drilling is horizontal drilling. In many ways, it increases production of well drilling. It's one where that exceeds 80-degree angles, like that one. That one's 90 degrees. But when it exceeds 90-degree angles, that means it's going up because it probably has missed a few particles of the rocks. This is a video that I will be talking about this iron sort of bird. To start off, this is just a short 3.5-minute video. Oh, that's going. About hydraulic fracturing. This is just well basics. And this is sort of like a 3D cartoon thing about what it looks like, the wellbore and the something I can't remember. Well.
It's going.
It's going, it's good. Well, the initial wellbore is drilled using a drill pipe and bit, which is this. And then mud is pumped down through the pipe to cool the drill bit. Mud also helps stabilize the wellbore and carries rock fragments to the surface. And the drilling continues past the aquifer level, or groundwater level, whatever you want to call it. And at this point, the drill pipe and bit are removed. A steel pipe called surface casing is placed inside the well. The casing protects the wellbore from groundwater reservoirs. Cement is pumped through and out the casing to drain any remaining fluid that keeps the casing in place. It also keeps groundwater from being contaminated and keeps things from entering the well flow. The casing gets a pressure test to make sure it's securely in place and keeps it in good formation. The pipe and drill bit are lowered back into the well where drilling continues. It should. Another layer of casing is placed into the first casing to make sure that the well is secure enough. And about 500 feet above shell formation, horizontal drilling starts to penetrate the gas or oil penetrating shale. And then a perforating, more cases performed when the horizontal drilling is done, like that. A perforating tool is placed into the well, creating holes in the shale, allowing hydrocarbons to enter the well stream. Take a while too far ahead. There we go. And when perforating is done, fracturing fluid made mostly of sand and water is pumped into the well, opening tiny fractures in the shale. Like this. The water is removed, but the sand stays, holding the fractures open, allowing gas to escape from the shale into the well. And then plugs are inserted to block the gas or oil from getting out. And once the fracturing is finished, which is what these are, the plugs are removed and allow gas to escape to the surface. The fracturing process can take up to 3 months, but hydraulic fracturing can only take up to a few days, and allow 30 to 40 years of energy production. Combining hydraulic fracturing and horizontal drilling allows drilling as it is done today to reach places past drilling could not. And I was wondering what shale is. I think she's got it covered. I'm doing the oil and gas traps in the wells. Okay, the oil and gas traps are deposits found in sandstone and limestone. A piece of limestone is very much like a hard sponge, full of dirt but not pressable. The porosity is permeability. Porosity is a measure of how much a rock has an open space. This area can be between grains or or cavities of the rock. Permeability is a measure of the ease with which a fluid can move through coarse rocks. This one right here on the tight, it makes it harder for the gas or the oil to leak through, and on these two, it makes it easier for it to move through the holes.
Okay, so I'm pretty much just explaining the casing. The conducting casing is the steel pipe that gets laid first. And then you have your surface casing, and it's the pipe that separates the conductor casing from the water. And then your cement gets put in to like hold everything in place. And then the performing well is the gun that shoots the holes through the casing to begin the fracking, and then your plugs just pretty much holds everything in place and prevents like everything from leaving until it's ready to be like drilled.
My name is Pablo Rustos,
I'm Kelly Reynolds.
and we'll be talking to you about the process of fracking, as well as how oil and gas recovery differ. We also have to apologize in advance because one of our group members was ill today, so we'll be trying to fill in for her part, but we'll do the best we can. Alright, so there's multiple steps to hydraulic fracking, and it's a rather complicated process. However, something I do is pretty simple, and as they were saying earlier, we have initially a well that's already drilled, and then what happens is we go down and they start drilling past the shale layer through the impermeable rock, and they start fracturing horizontally in order to get some of the fuel that is beneath the shale layer. So this is what your well is going to look like, and they'll have pipelines leading to holding units to store any of the fuel that they do receive. And then you see there, you see the trucks that they'll be using massive amounts of water, about 5 million gallons per frac, but this is recycled. So here we have the perforations, and these are the fractures being kept open by the sand that's delivered by the gel. So once these are holding open the fractures, it allows for easy flow for fuel and recovery of any fuel underneath the shale layer.
And then I'll be talking about what is hydraulic fracturing. Why do we do hydraulic fracturing? We hydraulic frac because we want to get the natural gas out of the deep shale formations. And we also do it because if we hydraulic frac, then we don't have to rely on foreign gas. But if we have to rely on foreign gas, we would get the gas from the former Soviet Union, Europe, Asian, and countries, the Middle East, Central and South America, Canada, Africa, and Mexico. And it burns cleaner because the natural gas is a water vapor and it has carbon dioxide, and carbon dioxide is what we exhale, and that's why it's considered clean. And it mainly is comprised of methane, and we get about 140,000 barrels of natural gas a day. And it helps the economy because it gives other people more jobs. And it comes faster, so we won't, and because like the gas won't move without us fracking it, and we can get more out of the oil. We can get more gas out of the oil wells.
It also secures our energy independence, so if we're producing more of our own fuel in our country, we're not spending more money in other foreign countries.
And fracking can be traced back to the 1860s. And in 1947, Systema and Oil conducted the first experimental fracking with the gel gasoline, and the actual fracking started in 1949. And Halliburton conducted the first two commercial hydraulic fracturing treatments. Right, and some more history is that there's 2.5 million fractures that exist around the world. I don't know when, but we stopped using the gel gasoline and diesel, and now we use guar gun, and that's a polymer. And there's more than 700 TSCF gas added since 1949, and we're working on making 100% edible treatments. And this is a map of where the shale is in the United States. Okay, and this is a video that we made of the test that we did. Yeah. Okay, so what he's doing now is he's putting in 400 milliliters of water, and then he adds 1.5 grams of the guar, which was the polymer, and then we mix it up.
Guar can be found in things like chewing gum all the way to hot sauce, so it's really common and edible. So what we're doing right here is we're just mixing the guar powder into the water, and this sets it up very nicely for the crosslinker, which Kelly will explain.
Yeah. And then now he adds 0.1 grams of the breaker, and the breaker is what makes it turn into the liquid that we need. And a breaker is a sodium persulfate. And the last thing he's adding is the buffer crosslinker. The crosslinker is what makes it turn into the goo. And the the mixture mainly consists of 99.6% water. And then, sorry, go ahead.
The crosslinker is basically bridging all the polymers together through ionic bonds, so they can be broken, but they do provide a lot of viscosity, which is needed to deliver the sand into the fractures.
And we're just testing it to make sure that it goes good.
And as you can see, it's extremely viscous. You can, if you have a very good batter, you can actually pour like almost the entire thing out, and it'll just come back into the pitcher.
And what we're doing now is we're testing it, and our group tested the temperatures, different temperatures. So for this one, it was 138 degrees. And then, since now it's done, the test took 96 minutes to complete, and it's a complete liquid now.
And because of the breaker that we added after the polymer, when the heat is associated with the gel, then it makes the breaker react either faster or slower. So it's going to take apart those those ionic bonds between the polymers, and it'll make it break up. And that's needed in order to actually get the fuel out of the ground.
Yeah, and the less the longer it's gonna take for it to turn from a gel into a liquid.
And also considering the massive amount of pressure and heat below the ground, you usually want to have it rather heat resistant for a time, because eventually it is going to break because of the heat and the breaker. But you do need it to be viscous long enough to deliver the sand and to keep the fractures open.
That's yours?
Oh, I have to do my slides after the copy. So with fracking, it especially provides a very nice transition to natural gas, and natural gas used in cars to powering our lives more than it does so now. And so understanding the differences between oil recovery and gas recovery is important, because it can bring to the surface some benefits or some non-benefits of gas recovery, just because it might be easier. All right, so there's primary, secondary, and tertiary, and these are the oil recovery steps. Next slide. In a normal derrick, you're going to have primary recovery gets you about 5 to 15% of what you could receive in the ground of fuel, and that's okay. With primary recovery, you're really depending on the natural pressure of the ground, of the geology, because miles underground, you're going to have tons of pressure, and that's just going to allow for the fuel to come out once the permeable layer is reached. Next slide. Secondary recovery is when you can no longer rely on the pressure of the geology, so you're going to have to synthesize your own pressure, and this is going to, so you'll be taking off where the natural pressure ends. And so you'll be adding more pressure. In this example, you have CO2 being pumped into the ground. This is providing more pressure and allowing the fuel to have easier access to the surface. And this gets you to 35 to 45%, or 30 to 45% of the fuel that you could potentially receive from the well. Next slide. And then tertiary recovery is usually used when the price of oil is much higher, because it's not exactly cost effective. What they can do is they can have steam injected into the ground. They can also do it with CO2 as well. This really gets anything that might be left or anything that they possibly could recover from the well. So with steam injection, it's going to create more pressure. It's going to make the oil hotter, so it's less viscous and it can be extracted easily. But you only get 5 to 17% of your possible fuel that is whatever's left down there. Next slide. With gas recovery, it's much different in that it's supposed to be a picture of the movie Up with the balloons, and that's to represent the buoyancy of natural gas. Google Docs is weird. Anyway, so Natural gas usually accompanies oil. However, you can just get natural gas deposits under the shale. And its buoyancy is what makes it rather beneficial for a source of fuel, because rather than having not only the pressure of the ground push it up, you also have the fact that because of its buoyancy, it wants to go up naturally. So once you break the permeable layer via fracking, then it's going to be very easy to extract it. There's crude oil wells, gas wells, condensate wells, and these are where you're going to find a majority of your natural gas. In condensate wells, you're going to find a lot of highly condensable hydrocarbons. Next slide. And there's two types of natural gas. The ones that are usually mixed or associated, and geologically they're very close to the crude oil, so they might actually be mixed in with it or very nearby, and it's very hard to see what's what. But then there's non-associated natural gas, and that's when it's not either mixed and there's little to no oil associated with it. So I hope this makes you understand that with fracking and the potential benefits of just natural gas in its physical traits, that is definitely a benefit for fuel, because it's easier by itself, and with fracking it's that much more obtainable. And that's it for us.
I'm Sasha Palmer.
I'm Kayla Pike. I'm Catalin Gonzalez.
I'm Dallas Goff.
Alright. Well, polymer, known as GAR, is in chewing gum, foods, clothing, a whole bunch of stuff. And it's a chemical too. Polymers are large molecules, which I'll go over in a few. Polymers are made up of different monomers. The different amount of monomers makes cross-linked, branch, linear. Okay, a monomer is a small molecule. Right here, there's one monomer, and with those three molecules can branch out to make another polymer, which equals a polymer, and this can become a cross-linked or linear or branch. And as you can see right here, that's linear, branch, and cross-linked. Linear helps for the heat when you burn it. It heats it up, which makes it melt and makes it reshape, which right there, it's just one straight thing. It doesn't have any connections or anything like branched or a cross-link. Branch has like a tree root. It has all these branches coming out, or like a tree has branches. Without these branches, it makes it like a linear. With the branches, it makes it the heat to not make it go faster and dissolving and going away. It keeps it connected and more structural. Next. Cross-linked, it's the same thing, but it doesn't have an ending, it doesn't have a beginning, it's all connected. And this one, if you put heat into it, it's not going to melt down, it's not going to form into a new formation. And then those are the chemicals that include into a whole bunch of chemicals that you need for hydraulic fracturing.
I'll be talking about helps dissolve minerals and initiates cracks in the rocks. Antibacterial agent eliminates bacteria in the water that produces corrosion byproducts. Breaker allows the delay in breaking down of the gel. Clay stabilizer prevents formation clay from swelling in the cracks. Corrosion prevents corrosion of the pipes, which means breaking of the pipes. Crosslinker maintains fluid viscosity as temperature increases. Friction reducer that slips the water so to have minimized friction. The gelling agent thickens the water to suspend the sand. Iron control prevents perspiration of the metal in the pipes. The pH adjusting agent maintains effectiveness of other components like crosslinker. Scale inhibitor prevents scale deposits downhole and in surface equipment. And surfactant increases the viscosity of the fracturing fluid.
Alright, so off that list, one of the main ingredients that we put into our gel that we had to make, as stated in the problem statement for shine and distill, to help flow everything in the fracturing process and out. Breaker reacts with the crosslinker to keep its formation in the heat and everything else underground because it gets really hot down there. The breaker even helps it make it easier to flow through the cracks in the pipe. Okay, surfactant increases the fracture fluid, and it even helps the other chemicals in the water to get up to the surface after the factoring has been done to get the oil out. Then we got Halliburton. They use all these chemicals in their factoring process.
Okay, so Halliburton does hydraulic fracturing. It was found in 1919. It is one of the largest oil field services in the world. It employs more than 70,000 people in approximately 80 countries. And hydraulic fracturing was first pioneered by Halliburton in the 1940s. John Sherlin, he was a guest speaker that came in and talked to us. He's a chemical engineer. He worked for Halliburton for about 20 years, and now he works for Anadarko in the Salt Creek field. A chemical engineer is pretty much the study of applied mathematics, material and energy balances, thermodynamics, fluid mechanics, energy and mass transfer, separations technologies, chemical reaction kinetics, reactor and process design. It combines chemistry and engineering concepts and is responsible for the conception and design processes for production, transformation, and transportation of materials. This is a video of when John Sherlin came in. He explained to us how to make the hydraulic fracturing gel. So here he is measuring the guar, or the polymer, and he is measuring 1.5 grams of that. And then inside the blender already is 400 milliliters of water. And so he will mix the guar in with the water and blend that for a few seconds.
And then here he's measuring the breaker, and he needs 0.1 grams of that. And then he will go ahead and mix that in with the already mixed guar and water. And blend that for just a few seconds as well. And then he'll get the cross linker. It's a syringe, and it's a 1 milliliter? 0.1 milliliter? 1 milliliter. And so he'll put that inside of there. And if you watch closely, you can't really see it very well in the video, but if you watch closely, as soon as he puts the cross linker inside of it, you can see the gel actually start to form after it freezes on. But pretty much from here on out, it just shows how the gel starts forming, and then it shows him transferring it back and forth between two beakers and how it won't fall out because it's not broken. And then he puts it out on his hand, and he explains how it doesn't leave any moisture at all. It's kind of like slime. And then Dallas will talk to you more about the lab itself.
Here we're mixing together the gel. First you have to have 400 milliliters of the water, then you add 1.5 grams of the polymer. Then we added 0.1 grams of the breaker and 1 milliliter of the crosslinker. And once we did that, we have to mix it up for about 15 minutes, and then we have the gel. The purpose of this lab was to see how each ingredient in the fracking gel affects the amount of time it takes to break. This is important because we need to get everything done underground before the gel breaks. It eventually has to break once the sand is in the cracks, so the liquid can be taken out and the sand gets left behind. Here's a lab that we did mixing up the gel. It was 0.5 grams of the polymer. It's pretty liquidy. It was very liquidy, and the gel broke at room temperature. This polymer, we have 1.5 grams of polymer. This is the original amount of polymer that we would use on a job. Here we have 2 grams of polymer. This polymer was somewhat broken down, but it was not liquid-like. The 0.5 grams of polymer I showed earlier. Here we have 2.5 grams of polymer. This gel is a lot more solid and condensed. It's compared to the other gels that I showed earlier. Here's a graph that I made of when we made these gels. Here's the 0.5 grams of polymer, and it broke at room temperature. Then here we have 1 gram of polymer, and it broke in 20 minutes. And then there's the 1.5 grams of polymer, which broke in about 25 minutes. And 2 grams of polymer, which broke at 15 minutes. And then you have the 2.5 grams of polymer, which broke at in 5 minutes.
Alright, so really quickly, this is our experiment, and what we dealt with was the heat. So we had the same amount of ingredients, just like everybody else in their experiments, and we just added different amounts of heat. So we had 3 tests, and as you can see, it's really obvious that the more heat you have, with the same amount of breaker, it's going to disintegrate faster and turn into liquid. So you see here at like about 135, it took almost an hour to disintegrate, and as opposed to 182, it took about 9 minutes, or 19 minutes. And so that kind of shows the amount of heat and just what effect it does have on the gel, and it's important to account for this in order to calculate exactly how much viscosity you need, and geologically where you are, you might have less or more heat, less or more pressure. So as far as heat goes, you can base what kind of gel you need off of experiments like this. Although this is really simple, it does embody that idea.
Okay, so controversy. Controversy stretches in a range from jobs, health, environment, and energy. Hannah, Reese, Chris, and we explain to you what it is that each of these things really are, and hope that you all be able to meet in the middle of the controversy. Now, the reason why jobs are so controversial is because there are so many jobs that involve hydraulic fracturing. Without hydraulic fracturing, we'd be hundreds of thousands of jobs without. And we'd be without multiple things such as refrigerators, our wall heaters, we'd be without grills for food, we'd be without our furnaces, dryers, and stoves. There's so many things that we would just be without if we didn't have hydraulic fracturing. Alright, so the one thing that we start off with is our oil company. So let's say our oil company is ExxonMobil. ExxonMobil will hire a contractor. This contractor will hire everybody else. And it ranges from hiring geologists, your coordinators, your petroleum engineers. Alright, so your geologists. Your geologists are going to say, when they come in, where the perforation needs to happen, how much pressure needs to be used, how much water, and everything. Coordinators are the people that basically run the whole show. They're going to say if there's 5 different trucks, they're going to be like, okay, well, I want trucks 1 through 5 to open your valves so that you can release a set amount of sand, water, chemical. Your petroleum engineer. They determine the way in which a reservoir is developed and depleted as well. Basically, they explain how well or not well the job is doing, and if the fracking needs to be stopped or there needs to be more pressure, it's something of the sort. Now you have your petroleum geologists. They will find the oil deposits within the shell rock. They'll tell you coordinates in which is it that you need to drill down and into the shell rock. And they work with machinery, science as well, and they kind of work with a little bit of everything. Alright, so your mud engineers, so your basic drilling. You're going to drill down that hole. They take care of the drilling fluids or the drilling mud. Your chemical engineers. Your chemical engineers deal with converting raw material into a basic material, such as chemicals. They deal with design plans. They also deal with equipment on plant. They are basically scientists of the fracking job. They constantly make gels so that everything is fine and running smoothly, And Darren Sherlin was actually one of those people, or is actually one of those people, and the person came in contact. Alright, so you've also got your truck drivers, your operators. They get your sand, your water, your chemicals. They got a pretty simple, but they from when they get there, your coordinator tells them what to do. It's pretty simple. And smaller jobs, such as cleaners, welders, and extractors, the cleaners will come in on the job, and if you have any small spills or larger spills or cleanups afterwards, clean that up. You've got your welders, which will build your derricks, trucks, anything that is needed to basically get the job done and going. You got your extractors for your sand, your water, and your chemicals. You have it all for your hydraulic fracturing job. And now there are also energy parts of this, and Grace will be explaining more on that.
So the whole point of hydrofracking is obviously get oil or natural gas out of the ground. So once we get out of the ground, what are we going to do with it? We're going to create some energy with it, and then that energy or electricity will go to your home. So natural gas is the cleanest fossil fuel in the world that we know of right now. It releases 30% less carbon dioxide than oil does and 45% less carbon dioxide than coal does. And you can see right here that natural gas is lower in everything than oil and coal is, except carbon monoxide and oil. So it beats out coal and oil, which are the other two main fossil fuels that we use. And in this graph here, the blue line is coal, and this brownish line is natural gas. So you can see that our natural gas usage is starting to go up, and our coal usage is starting to go down. So some people have caught on that natural gas is better than coal. So natural gas is about 60% energy efficient, which means out of the maximum output that could possibly happen, we get 60% of the energy to our houses from natural gas, while coal and oil are only 30% efficient. So another type is solar, and as of right now, it's only 10 to 20% effective, but some experimental cells have reached up to 40% efficiency. But natural solar cells don't last very long. They just wear out too fast. So some scientists have actually started using nanocrystal technology to build new solar cells, and they have reached up to 60% efficiency. But to put them into a large-scale production will take years. We're still far behind. And it is about $1 per kilowatt hour, which is pretty expensive for energy. But the U.S. consumed, out of all the energy we use, 0.1% was solar. And out of all the energy we produced in the U.S., 0.04% was solar. So we're far behind the curve on solar. The next one is wind. And in the Midwest, which is the windiest place in the entire U.S., the wind only blows 60 to 90% of the time, because it doesn't blow all the time, obviously. And as efficient as they are, they only capture about 60% of the wind. So that's nearly half the wind that's just getting off and that we can't use. So it's only about 30% efficient, which is still far behind 60% where natural gas is. And it costs 2 to 3 cents per kilowatt hour because it is basically an unlimited, infinite source of energy. We will never run out of wind, as most of us probably know. So, out of all the energy produced in the U.S., 2.9% of it was wind, and out of all the energy used, we only used 1.2% of wind. So it's actually doing pretty good. We produce a lot, but we don't use a lot. And coal is obviously Wyoming's biggest production, so coal's kind of important to us. But it only averages 31% efficiency, which is pretty bad. And it costs 4.8 to 5.5 cents per kilowatt hour, which is a little more expensive, but that's because it's a finite amount. There's only a certain amount in the ground. And as in the graph before, you can see that we're starting to use less and less coal, which means less emissions, but not enough export for Wyoming. And all the emissions from coal burning in the United States is more than all the transportation in the United States. So all the cars, buses, trucks, airplanes, all those emissions, coal beats them all. Next slide. But probably the best for the environment is nuclear because it has no emissions or pollutants, and it only costs 2.19 cents per kilowatt hour, which is the cheapest fuel. But nuclear power plants are expensive to get started. They're several $1 million to build, and they're dangerous and radioactive and everything. But as long as you can keep them contained, they're pretty good. So nuclear energy only provided 9% of all the energy in the United States. But it is a 98% efficiency, which is probably the best for the environment. But to talk more about the environment to you is Chris Liver.
Okay, so as most of you probably know, natural gas is composed mostly of methane. And Cornell professor Robert Howard believes that 3.6 to 7.9% of methane from shale and gas production is released through venting and leaking over the lifetime of a well. Howard went on to say that compared to coal, the footprint of shale is at least 20% greater. But MIT researchers found that replacing coal power plants with natural gas plants could reduce carbon dioxide by more than 50%. Because it burns cleaner than conventional coal. And so basically, coal and oil are made of more complex molecules. When they combust, higher levels of more harmful emissions are released into our atmosphere. But, okay, so the environmental impacts reach way further than just the air. It's also our water that's being affected. And the Natural Resource Defense Council, or the NRDC, says opponents of the NRDC claim fracking has never caused any water contamination. They say this because incidents where hydraulic fracturing is being considered suspect have not been significantly investigated. But then the writer of the NRDC goes on to list 37 different instances where hydraulic fracturing is believed to have contributed. Okay, toxic chemicals. So 98% of the makeup for fracturing fluid is water, right? And then 2%, measly little 2% chemicals. But in a 4 to 5 million gallon fracking operation, that could be like 80 to 400 tons of chemicals. In 2010, the EPA estimated 70 to 140 billion gallons of water are used to make 35,000 frac jobs per year. Jack Healy of the New York Times wrote, a single such well could require up to 5 million gallons of water. And then the EPA went on to say, in some cases, less than 1/3 of the water is recovered after a frac job. Oh, farmers versus frackers, right? Jack Healy didn't just talk about the amounts of water that are being used, but he talked about the vast disadvantages that farmers in Colorado have against the companies who frack. Peter Anderson, who grows alfalfa in eastern Colorado, said it's not a level playing field. He said this because him and other farmers in Colorado, on average, pay about $30 per acre of water, and that's equal to 326,000 gallons of water, right? When water's scarce, it's like $100 per acre. But oil and gas companies right now are paying as much as $1,000 to $3,000 for the same amount. So that's pretty easy math for the city, right? Their earnings alone for this year are going to be about $4 to $5 million. This one's just a lot of my sources because it's controversy stuff. I thought you guys would want to see that, but I'm not making this up. And I'm not trying to, like, it might sound like I'm trying to favor one side, but I'm not. I'm only talking about topics that are being discussed. And from my understanding, it's not just the environment that's being affected by this, it's also a lot of health issues. And so maybe Ms. Hannah Hout can tell us some facts.
Usually when you hear people talk about hydrofracking on the news or something, you hear about the groundwater contamination and the health effects and what it's doing to the public. Next slide. Groundwater contamination. Some of the biggest questions is it really a public health concern? What is being done to prevent it, and how likely is it to occur? Recently, the Independent Oil and Gas Association, or the IOGA, offered up a study done by the University of Texas. In this study, many issues were addressed, such as groundwater contamination, toxicity of fracking fluid, surface spills, and water use. And 3 major areas were addressed: the environmental and health effects of all areas of shale gas development, the public perception of this process, including media coverage, and the state and federal regulations. At the conclusion of this study, they found that there was no evidence of aquifer contamination from hydrofracking chemicals or operations, and that no leaking was observed. Many reports of contamination were caused by conventional drilling methods, such as like faulty casing or bad cementing jobs, and that most methane found in water in the shale gas area could be linked back to natural sources and not fracking areas. And they said that surface spills are more likely to pose a risk to groundwater contamination than the hydrofracking process itself. And blowouts, while rare, are underreported. When they looked at media coverage, will you go to the next slide? They found that almost 2/3 of news coverage is negative. And they looked at how much scientific research was put into this reporting. They found that less than 20% of newspapers, less than 25% of news broadcasts, and less than 33% of all online papers published on this subject did not include any scientific research. Now, it's not just the public that we should be worried about. The CDC and other national agencies are also worried about the risk that this process poses to our workers. Right now, the biggest issue is silicosis, which is caused by silica dioxide, which is in the crystalline silica that they use as a man-made sand in some areas. Recently, NIOSH, or the National Institute for Occupational Safety and Health, took 116 samples from 11 different sites, from Texas, Arkansas, Colorado, North Dakota, and Pennsylvania. Now, before I get into that, silicosis is a irreversible progressive disease that cannot be cured. And over the course of several months or years, it hardens the victim's lungs, and they eventually die because of this. This is caused from inhalation, of silica. Now, the NIOSH RDL, or recommended exposure limit, is 0.5 milligrams per cubic meter, and that's the time-weighted average. So over time, they try to guess or estimate how much you're inhaling. And the OSHA PEL, or permissible exposure limit, is 10 milligrams per cubic meter, which is a little bit more. Okay, next slide. Sorry. 500 micrograms, or 0.5 milligrams, which is the REL, is that much, and that's compared to a dime. Okay, next slide. So 50 micrograms, or 0.5 milligrams, is how much you are allowed to breathe per cubic meter, which is about 1,000 liters of air. You normally breathe about 10,000 liters of air. So it's 50 micrograms times 30 meters cubed, which is about 500 cubic meters, or no, sorry, micrograms. Okay, next slide. Okay, so now out of those 116 samples, they found that 54%, or 47%, was greater than the OSHA permissible exposure limit. And 79% was greater than the NIOSH recommended limit. And 36 out of 116 were 10 times the NIOSH recommended exposure limit. I don't think I have any more slides. So going off of that, there are a lot of cons with this. There are kinks that still need to be worked out. Right now, Halliburton and Schlumberger are working with the CDC to make sure that their employees are always going through the correct steps to eliminate exposure to silica, because there are about 200 documented deaths per year because of silicosis. And there's a lot of different ways that this can be inhaled, and it's usually just easy things to avoid. They can use their ventilators correctly. And I hope that this has helped you guys see that this is not a black and white issue, and it's not necessarily an issue at all. That there's a lot of gray area, just like there are in a lot of other things that we do to produce energy, and it's not always as easy as just picking one side or the other. Thank you so much for coming, and if you have any questions, we would be happy to take them.
Questions?
You in the back, had your hand up first?
When you're comparing using the silica to sand, I didn't understand why they went to silica instead of sand.
It's easier to ship in some areas. Like here in Wyoming, we don't use it because we have the sand mines, or we have sand quarries around, and so it's easier for us to get sand. Or we use ceramic beads in some cases. But in certain areas, it's easier to make the sand because it's cheaper and we can pump more of it in, and then we don't have to worry about other factors. So, and it's only some states that use it mostly, but Wyoming, we don't use it here, so.
Well, I thought it was really interesting because I hadn't heard about the silicosis or the silica issue. Around here, it's always the water. Did you guys find any
Yep.
issues with water around here?
Well, of course, there's the pavilion incident.
I wondered if you,
Yeah.
that was my next question.
That's such a controversial issue. There's a lot of reasons that could have happened. You guys want to go into that? Explain that? I know
The
they don't have
wells
it.
are like 50 years old if the gas is coming out of.
I'm sorry, I didn't hear.
The wells that the gas is supposedly coming out of are like 50 plus years old.
Yeah, so they might have faulty cementing, they have any cementing at all, and faulty casing. Yes.
However, they found some tracers that didn't exist 50 years ago in their analysis. And the problem with that is that if those tracers came in yesterday, or a year ago, or when they were doing that, then it's a smoking gun that the industry is actually polluting something. Most of the pollution in Pavilion is probably natural, though. They've always had that problem with methane getting in there. But the question I have on your water or your sort of like a cooking sauce, what you talked about how they prepare all this, and you talked about how they use it. But what happens to it afterwards? What happens with the water? We saw a picture of a reservoir with a liner, but what happens to it?
Well, there are a couple of things that can happen. Either one, they recycle the water. Halliburton does this a lot because it does have some chemicals, but then again, you also have to factor in that a majority of those chemicals are either so diluted they're not harmful, and they're actually, some of them are edible, like the guar gum. And if they can't recover all of the water, they will leave it down in where they fractured, and it won't have a tremendous effect, if any at all.
And for those companies that don't recycle their water and don't recycle their fluid, they do dispose of it the way that the CDC asks. And there are teams that if the chemical's still on the ground, they're out there, within hours to pick it up before it can soak into the earth, to make sure that they're doing everything as environmentally conscientious as they can, to make sure that they're not damaging the area that they're working in. And there are teams that specifically come out and they clean the chemicals and they dispose of it the way that they're supposed to after Halliburton leaves or after some of the representatives leave or something.
You had a question, ma'am?
Yeah, well, first I have a statement, and this is a biased statement because I'm from oil. My father was in oil, my husband was in oil. But OSHA has more regulations for the natural gas production and oil production for our oil workers than almost any other kind of company that we run in America. And so, the reclamation is not just involved with the company, but is involved with the people that own the land and with the state. So the reclamation, my father had to go out and tell you every artifact, every bush, every little plant, and then they had to redo it just like that. So that's just my information on that. Also, I wanted to ask about the breaker. You guys talked about the heat of the breaker. Pablo, you talked about it, and several of you guys did. What does that, I think the longest time that it went on your chart here was 15 minutes? Is that correct? 10 minutes?
Actually, that was the shortest time because
Okay, so what's the longest time?
about 54 minutes.
So right from the time they frack, are you using that on a fracking well, that by the time they frack, they only have that long? What was the purpose of that?
It really depends on like the heat of, because in some areas it'll be hotter or colder. That was just like an example to say that they can modify it, say maybe this is hotter, we don't need as much break.
I see. Okay, thank you.
Yeah.
Just a comment on what happens to the fluids out of a well. These days, most of your wells, particularly your horizontal wells, are drilled with oil-based muds. And what they do with that after the well is finished is they use centrifuges to spin out the heavier particulates, and they reuse that over and over and over.
Yes.
So it just doesn't really go away. They just keep recycling it and adding back the appropriate chemicals and whatever it is that they need to add to that drilling mud or drilling fluid almost indefinitely. So when they do use a water-based mud or drilling fluid, they just simply let it set in the pit until it dries up, and then they cover it up. They have done tests to see what works best, where they literally till the soil, take that drilling mud, spread it out on the soil, till it into the soil, and the drilling mud has little to no effect on what it does. In many cases, it enriches the soil.
Can't beat it.
Can you be a little bit more clear? I know you talked about fluid quite a bit, and quite a few of you talked about the fluid and the cross-linking and all of that. Could you explain where the sand fits into all of that, and why, I mean, we didn't use sand in our lab, but explain the sand part of the fracking fluid?
Well, so it's basically a gel that goes down because water can't carry sand. But, so it's got to be viscous enough to carry the sand down into the cracks to create permeability in impermeable rocks. So it's like if you put a jar of marbles down and you put water in them, eventually the water will get to the bottom of the cup or whatever the marbles are in. And that's the point of the sand, is to hold open the cracks so that the oil can flow through the little holes between the sand and go out through the pipe.
Yes, Adam, you have a question?
So the polymer, how does the pressure underground affect the polymer?
Well, the pressure is also going to create some heat, and deep underground, because of its viscosity and because of just like the structures of some of the polymers, it can really be very pressure resistant, and so it won't have a drastic effect. It won't condense, and it won't like get to the point where it's not functional anymore. And so viscous, let's say, okay, maybe Jello isn't the best example, but pudding. It's rather viscous compared to water, and you can set M&Ms in pudding and it won't sink to the bottom for like 1,000 years. But if you do that in water, it'll sink straight through. So imagine the gels being similar to pudding in that strange analogy.
Another thing on the polymer is because it is a polymer, if it breaks, it can link back together. Because the monomers, they're individual and they are able to link back together. So if the pressure does happen to break it, if that polymer is able to come in contact again, it links back together and fixes itself. So
And in the example we showed you on the video, you could actually tear the gel apart, put it back into the jar again, and in a couple minutes it would be again connected. So it kind of repairs itself in that manner. Yes.
I was curious if your group, when you were researching horizontal drilling, that's something I've always was curious about.